The next thing we're going to look at is phase changes. Phase changes describe the transition, for example, from solid to liquid, or liquid to gas, or solid to gas, or gas to solid. Depending on which transition it is, they're called by different things, but they're all related to these changes in energy. This is a graph of the heating of a substance as it passes from being a solid on the left-hand side of the graph to a gas on the right-hand side of the graph. During the phase changes, we have solid to liquid here, we have liquid to gas here. You'll notice that those phase changes are taking place at constant temperatures. Those are true horizontal lines. The temperature does not change during a phase change. Now, if you think about the fact that we have talked about in previous chapters that kinetic energy is proportional to temperature, if the temperature is not increasing, the energy that we are adding as heat must be going into something else. And of course, the only other thing there is potential energy, and we find that that is what is happening. So as the temperature is increasing in the solid, in the liquid, in the gas, we are increasing kinetic energy. As we go through phase changes, we are changing the potential energy. During the phase change, the phase change is symmetrical with respect to heat added. So going from right to left on our previous diagram is the reverse process of going right to left. So if we are adding heat as we move to the left, we remove heat as we go to the right. We have to remove the same amount of heat to go from the liquid to the solid as we have to add to go from the solid to the liquid. We find that the amount of heat that we have to add is proportional to the mass of the sample involved. More mass, more heat. We find that the amount of heat that we have to add for a phase change depends on the identity of the sample. The process of fusion is going from a liquid to a solid, and it takes the same amount of heat to go in reverse. So we call that the heat of fusion. And to go from a liquid to a gas is what we call the heat of vaporization, and that's how much heat we have to add to make the transition from liquid to gas. It's how much heat we have to remove to go from gas to liquid. Here we have all of that displayed in a nice compact formula. The amount of heat, Q, is equal to a constant that is related to the material involved. It's called either the latent heat of fusion or the latent heat of vaporization. And we abbreviate that usually with either an L sub F or an L sub V. Some texts use a H sub F or H sub V, but we're using L's. And M here stands for the mass of the sample. You'll notice, of course, that there is no inherent temperature change, so there is no delta T term. We just have our heat added, our property of the material, and our amount of the material. And the constant of change depends on the identity of the material. And here is a summary table that shows some heats of transformation. So you'll notice here again, water is in the middle of this chart. It has a melting point listed as 0.1, although using a melting point of 0 is perfectly fine for everything that we do. The heat of fusion is 333. Note this is in kilojoules per kilogram, so it's also joules per gram, or you would read that as 333,000 joules per kilogram. I emphasize that point because specific heat tables are usually given in terms of joules per kilogram, or joules per gram, or calories per gram. So the order of magnitude of these numbers is much larger. It takes a much larger amount of heat to convert solid ice into liquid water than it does to heat the water or heat the ice beforehand or afterhand. And notice that the specific heat the heat of vaporization is enormous for water, even in comparison to its heat of fusion. That is generally true. It takes more heat to convert the liquid into the gas than it does to convert the solid into the liquid. And when you think about it, that makes sense, because energetically you're actually pulling molecules off of the surface as opposed to just breaking the bonds and making the substance mobile. But this is very important. This heat of fusion and heat of vaporization is hidden. It's latent heat. It goes into potential energy, whereas the specific heat goes into making the molecule vibrate faster in the case of solids, or meander faster in the case of liquids and gases. These transitions require a tremendous amount of heat. Yet another reason that water is an excellent cooling fluid: it takes a lot of heat to boil away your water.